A propeller for a 400-meter container ship can remain 25 years underwater with little opportunity for direct human access. Inside the same ship, the crankshaft spins through millions of torque cycles, year after year. Salt, pressure, and load will spend that entire working life looking for the smallest mistake left inside the metal. Stay until the end, and you will see exactly what engineers do to make sure the ocean never finds one. The sea does not destroy metal in one blow. It returns to the same weak point again and again until something gives. A part does not have to fail on its first day. It can fail after millions of ordinary turns, each one removing a little more of what holds it together. On a drill ship commissioned, 6 thrusters run continuously, 24 hours a day, 365 days a year. Each rotation loads the metal, unloads it, and loads it again. That endless cycle is exactly what fatigue feeds on. After enough of it, the thrusters have to be exchanged to keep the integrity of the station-keeping system that holds the vessel in position over a well. The replacement is its own engineering job. 3 thrusters were newly built in one workshop, 3 rebuilt in another, then shipped to a single port for the swap. The vessel arrived for its special periodic survey, with underwater inspections standing in for dry docking. The big lift came after a year of preparation. Each thruster weighs around 60 metric tons, lowered into the water by heavy rigging, and the team had only 24 hours to connect each one to the hull. 2 divers worked the connection by hand, fitting heavy shackles in open water with a standby diver always ready. Once seated, each thruster is filled with oil and proven during sea trials before the vessel returns to work. While fatigue works from inside the metal, the sea attacks the surface from outside, slowly and chemically without stopping. A diver descends to a large propeller still mounted under the hull, carrying a hydraulic polishing tool fed by a line from the surface. The blades have gone dull, coated in marine growth and the staining that seawater leaves on bronze over months in the water. Working blade by blade, the diver grinds the fouling away, and clouds of loosened biological matter drift off into the water around the tool. The work moves from the outer edges inward to the blade roots, where the buildup clings hardest. A rough, fouled surface drags through the water and forces the engine to burn more fuel. A polished blade cuts cleaner, runs smoother, and is read more easily for the early pitting that corrosion and cavitation leave behind. The most dangerous flaw is the one that passes inspection just long enough to grow. And on the parts that turn day and night, that growth never stops. A reconditioning workshop shows what the sea and the engine room do to metal over time. A crankshaft, the spine of a diesel engine, sits in a machining center, having its journals and crank pins reduced and rebuilt to the customer's required dimensions. The grinding of the fillet radii is treated as one of the critical steps because that is where stress concentrates and where a fatigue crack would start. Nearby, a cooling jacket is being repaired and a cylinder block reassembled, both of them parts that live under constant heat and pressure cycles. Damaged crankshafts can even be reduced and rebuilt inside the engine using tailor-made tooling. Direct testing follows every repair, and different welding processes restore the worn metal because a part allowed back to sea has to be trusted not to fail mid-voyage. Some loads do not build slowly. They arrive all at once. A controllable pitch propeller system was supplied for a series of patrol boats. Unlike a fixed blade, its pitch can be adjusted while turning, which lets the crew change thrust fast when a vessel has to accelerate, reverse, or hold station in a hurry. Every one of those rapid changes sends a shock through the blades, the hub, and the shaft behind them. Every failure mode you just seen traces back to one place: the moment the metal was made. The defense against the ocean begins long before the part ever gets a shape. Inside one propulsion factory, the core elements of thrusters are cut from high-quality forged steel. Material science experts track how the metal reacts to displacement and temperature using sensors and finite element analysis before any part is finished. Before engineers can shape anything, they have to control the metal while it is still liquid, while there is still a chance to keep the flaws out. Heavy overhead cranes move a giant pouring ladle filled with glowing liquid metal into position above the molds. Engineers check the nozzle at the base of the ladle first, priming it with a small test flow to warm the system before the real pour begins. A second ladle, just as large, is brought in alongside. The two are positioned together over the feeder funnels of a pit mold sunk into the floor. The pour starts, throwing smoke and sparks, and the two ladles work in sequence to fill the cavity. Crews then read the slag at the mold mouth and watch the first cooling. Get the recipe wrong at this moment, and no amount of polishing later will save the part. A clean surface cannot fix a dirty interior. Casting a propeller starts with the alloy itself. Marine propellers here are built in brass and manganese alloy or in a nickel-bronze aluminum alloy, each chosen for how it stands up to seawater and load. The design is drawn in CAD, and a scaled plastic blade is 3D printed first, so the geometry can be checked by hand before any metal is melted. Workers pack special casting sand around steel frames. An industrial furnace melts the copper alloy into a glowing stream that transfers to a large pouring ladle. Two operators in full heat protection guide the ladle and pour the molten metal into the closed sand mold. After cooling, lifting chains raise the mold cover, and crews break away the surrounding sand with sledgehammers to reveal the rough casting inside. The raw blade then goes into a blasting chamber for surface cleaning, the first time anyone sees whether the pour came out sound or porous. The cleanest way to keep flaws out of a casting is to know exactly what went into it, every ingot, traced and certified before it ever melts. A propeller is the most harshly stressed part of any boat, so the whole process is kept under one roof and carefully controlled from start to finish. The foundry turns certified ingots into castings using induction melting furnaces, and it is approved by all the major classification societies, which means the material and the method are documented to an external standard. Skilled foundry crews use well-developed molding and casting techniques to get sound results from each pour. Design begins with computer programs that generate the propeller shape, and a patternless rapid prototyping process drives a computer-controlled machine to produce a pattern or mold directly from the data, turning a custom design around in minutes rather than days. A specially developed cavitation-reducing blade section is built into the shape itself, addressing one of the failure modes the sea uses most. Beyond propellers, the same operation produces shafts and stern gear with shaft diameters up to 400 millimeters. One contract shown supplies 50 propeller shaft systems, each 130 millimeters in diameter and 8 meters long, built to a classification society's rules. Every shaft is precision straightened before machining, because a shaft that starts bent never runs true in the water. A shaft carries the entire output of the engine down its length, so what hides inside the metal matters as much as what shows outside. A controllable pitch propeller shaft is hollow bored from a single piece, in steel or stainless, in lengths up to 14 meters. The bore runs concentric down the full length of the shaft. Coolant floods the cutting zone continuously, and the chips are screened and checked as they flow out, confirming the cut is staying stable through the solid metal. Some parts are built to be reachable. This is not one of them. A large ship propeller can stay in service for more than 25 years and can cost into the millions of euros. After installation, maintenance on it is nearly impossible, which puts the entire burden of reliability on the material and the build. Once the vessel returns to sea, the propeller is expected to keep working without direct access for years at a time. The propeller hub is engineered to minimum tolerances, and especially hardened metal is worked on numerically controlled machines to reach the precision and finish that let the parts assemble perfectly. The completed unit is then proof tested at 70 atmospheres of oil pressure, around 2.5 times the actual service load it will see at sea, and that severe test is run just 1 hour after assembly. Any weakness left inside the metal will eventually meet constant pressure, vibration, and seawater. A part that has to last a quarter century underwater, untouched, earns no second chances. Everything that protects it has to be correct in the metal first before pressure ever shapes it further. Casting gives metal a shape. It cannot give it a direction. For the parts that have to resist fatigue under millions of load cycles, the next step is pressure, where the internal structure of the metal is forced to line up with the forces it will carry. A North American supplier built a new vacuum arc remelting and electroslag remelting facility specifically for the open die forging, extrusion, and ring rolling industries. The investment topped $70 million and earned aerospace-grade AS9100 certification because forging customers cannot afford a hidden inclusion to be lengthened into a future fatigue crack. In vacuum arc remelting, an electrode is melted drop by drop, under vacuum, a process that takes up to 48 hours and pulls down dissolved gas, segregation, inclusion content, porosity, and internal cavities. The electroslag remelt furnace, the largest of its kind in the Western Hemisphere, runs each ingot through liquid slag drop by drop, removing the large inclusions that forging would otherwise turn into elongated weaknesses. The real work of forging is not making the part smaller, but making the inside of the metal harder to tear apart. An open die forging operation runs 5 presses, up to 5,000 tons of force, capable of handling forgings up to 110,000 pounds, 57 feet long, and 94 inches across. The clearest example of forging as a force management tool is the crankshaft. Get it right, and the engine runs for 1,000,000 hours. Get it wrong, and the failure is buried so deep no inspection at the factory will ever find it. A heavy crankshaft forging operation runs the kind of presses that can shape a single piece of steel weighing many tons while it is still red hot from the furnace. The starting point is a clean alloy steel ingot that has already been controlled for its chemistry. The ingot is heated to forging temperature, brought to the press, and worked under hydraulic pressure in repeated heat and press cycles. A manipulator on the floor grips the workpiece and rotates it between strokes, so the press can work the material from every direction and drive the deformation deep into the center. As the press strikes, the internal grain flow of the steel is forced to follow the geometry being created, running along the journals, around the crank pins, and through the webs that connect them. The result is a piece of metal whose internal structure is aligned with the load paths it will carry inside an engine, where each ignition stroke twists the shaft along its length and bends it across its main bearings. Between heats, the steel is allowed to cool in a controlled way, because uncontrolled cooling locks in residual stress and undoes the work the press has just done. After forging, the shaft passes into heat treatment to set the final mechanical properties, then into rough machining to relieve more stress, then into final machining, where the journals, the crank pins, and the fillet radii are brought to size. Every single one of those fillets is a stress concentrator, the exact place where a fatigue crack will start if anything earlier in the process went wrong. A forged crankshaft that fails at a fillet 10 years later was almost always built with the wrong force path from the very first press stroke. A crankshaft is built to handle torque inside the ship. A propeller is built to withstand the ocean outside it. Those two problems pull the manufacturing in different directions, and from here, the work moves into the casting yard, where the shape of metal has to be sculpted for the flow that will hit it for years. A modern container ship propeller on display weighs 82 tons, with a blade surface area of 42 square meters. The blades are noticeably slimmer than older designs, every curve tuned to a specific ship and operating profile. A single fleet upgrade across 13 ships, built around new propellers with matching hull and engine changes, is expected to cut fuel use by around 15%. The hardest part of casting a propeller is not the size. It is making sure the recipe inside the metal lines up with the job it has to do for the next 25 years. Inside an industrial foundry, workers run a high-temperature furnace to melt the alloy that will become the blades. The mix is held to a precise composition: 80% copper, 9% aluminum, 4% nickel, 4% iron, and 1% zinc, a nickel-aluminum bronze recognized for its resistance to cavitation in seawater. The molten alloy is poured into the prepared mold under technical supervision. After the metal has cooled and solidified, the heavy mold block is moved aside and a tracked excavator with a hydraulic breaker chips away the surrounding sand and slag. The rough casting is then lifted onto a large rotating bed, and a CNC cutter walks across the blade surfaces, removing excess material and shaping the hydrodynamic profile. Technicians mark the blade with measurement notes so dimensions can be checked against the design. A propeller is not poured into a generic mold. Each one is carved for the ship that will turn it. A propulsion plant in Drunen serves as a global knowledge center for the design, production, and service of fixed and controllable pitch propellers for vessels of every kind and size. Beyond the blades themselves, the same site supplies propeller shafts, stern tube bearings, sealing systems, transverse thrusters, rudders, steerable thrusters, and water jet systems to shipyards and ship owners worldwide. Propellers are cast on site using precision-carved molds prepared individually for each propeller, a separate mold for a separate ship. After casting, the finishing is not handed over to a machine. Hand grinding by experienced craftsmen brings the blades to the exact measurements and the designed properties needed for a sound service life, blade by blade, the surface profile slowly converging on what the hydrodynamic design called for. The same workshop also handles the repair and reconditioning of damaged propellers, which means the people grinding new blades have seen firsthand what happens to a blade after years at sea, and they shape the new ones accordingly. A propeller does not only have to push water, It has to do so without disturbing the rest of the ship around it. On a performance cruising yacht, the operator presses a control button. A hatch in the underwater hull opens, and a 5-blade bronze propeller pod lowers out from inside the hull and locks into position. A 3D animation shows how internal pistons drive the pod out and pull it back in. The pod can then steer left and right to test the azimuth function, and the propeller spins up under direct drive. When retracted, the hull closes flat again, giving back a completely clean underwater surface. A propeller does not work alone. It works in line with a shaft, a bearing, a gearbox, and a hull. And a small error on one of them shows up as failure somewhere else entirely. The propulsion system only works properly when every rotating part stays aligned under load. A vessel with 2 main 1,250 kilowatts thrusters and 2 retractable bow thrusters of 1,000 kilowatts each enters dry dock for a full propulsion overhaul. The thruster pods are dropped from the underside of the hull by overhead crane, lifted out and trucked to a specialist workshop. There, the housings are split open, the bevel gears stripped and chemically cleaned, and the vertical drive shafts pulled from their bearing seats. Mechanics measure clearances and geometric tolerance at every bolt circle, recut threads where needed, and check shaft seal surfaces by hand. The large bronze blades are polished to a high gloss, near mirror finish, so they cut through the water with the least disturbance, the surface chosen specifically to reduce cavitation. Each blade edge is checked against its profile by eye and gauge. Shaft runout is read on a precision dial indicator, because even 1/10 of a millimeter of misalignment becomes a measurable vibration at full speed. The bevel gear set is aligned tooth to tooth with mechanical fixtures, and every flange bolt is torqued to a recorded value. Only after a pressure leak test on the hydraulic control system, the rebuilt thruster pod are back under the hull. The propeller is the part everyone sees. Behind it sits a column of mechanical work that has to be perfect before the bronze ever turns. A finished Azipod electric propulsion unit is built up in steps. First, the large outer housing is positioned on the factory floor under an overhead crane, and the stator core of the electric motor is shrink-fitted into it, lowered vertically into the housing while engineers monitor the fit. The unit is then rolled onto a yellow tilting cradle and turned horizontal for the next stage. Inside the housing, technicians install the cable routing and the internal fittings. In parallel on the factory floor, the shaft line is assembled, with the rotor shaft mated to the motor core, the thrust bearing fitted to absorb the propeller's push, and hydraulic tools used to tension the large bolts on the shaft. Every rotating component has to stay aligned once the full propeller load begins traveling through the system. The whole rotor and shaft assembly is then lifted and pushed horizontally into the stator, sliding through the center until it seats in position. Cables are connected from outside the housing into the motor. The completed unit is tested at a digital control station, then lifted onto a heavy transport for the journey to a shipyard. At the yard, a heavy lift crane brings the entire Azipod under the stern of a large vessel. The unit is hoisted up, and the steering bearing at the top is bolted into the hull. The final step is the bolt-on of the large bronze propeller blades themselves onto the underside of the pod. Only at that point does the propulsion system finally become part of the ship instead of a standalone machine. The hull is now ready to launch. Forging and casting build the body of a propulsion system. They cannot finish it. The surfaces that actually meet the load have to be cut to dimensions a casting alone cannot hold. From here, the work moves to the machining floor. A horizontal turn mill center, built for complete crankshaft machining, shows how serious that task gets. The machine handles shafts and chuck parts in one setup, capable of high-volume automotive crankshaft production as well as smaller batches. The bed is cast from polymer concrete rather than steel, chosen specifically for its rigidity and its damping behavior, because vibration from the cutting tool will print directly onto the journal surface. High-quality linear roller guides hold the cutting head on a precise path, part after part, year after year. A high-speed disc milling cutter removes heavy stock from the journals and crank pins, preparing them for the finer machining steps to follow. A controllable pitch propeller blade enters the lathe. The cutting tool stops here. From this point on, the finish is done by hand, because even small surface imperfections disturb the water flow across the blade. A worker in full protective gear grinds and polishes a cast propeller blade by hand, working it down from a rough cast surface to a near mirror finish on the bronze. A part can be too large to lift by hand and still fail because of a surface too small to notice. Off Walvis Bay in Namibia, technical divers descend in a protective cage to access the thruster under the hull. Bolts are loosened, hydraulic lines disconnected, and lifting chains rigged. The thruster is hoisted up to the deck workshop, where the housing is opened. Workers grind off marine growth and split the unit down to the main shaft and the sealing rings. The components go into the machine shop for cleaning, wear measurement, and seal replacement. Only after rebuild does the thruster go back under the hull, where divers reseat it and torque the bolts. When the wear pattern crosses a line, the unit no longer gets reused. A bow thruster on a cargo vessel is cut free at the quayside. A diver rigs lifting chains inside the thruster tunnel. The shore crane lifts the old unit out, encrusted with growth and visibly worn, and drops it onto a truck. Divers grind the tunnel interior clean before the replacement bronze propeller and red housing are lowered into place. A surface that was perfect on day one will not stay that way for free. A wheeled cleaning unit is lowered to a container ship's hull, where a diver guides it along the steel. Rotating brushes strip away biological fouling in parallel passes, returning the underwater surface to something close to its design drag. The hull starts costing fuel the moment marine growth roughens the surface. A commercial diver carries a handheld brush cart system along the side of a vessel below the waterline. Pressurized cleaning heads work the steel in overlapping strips, stripping fouling without cutting into the anti-fouling coating beneath. Cleaning is done in the water, no dry docking required. Even the best surface means little if a hidden crack is sitting just inside it. The real question is whether the structure beneath the weld is as solid as the surface makes it appear. A diver tests the welding tool first, then fixes the workpiece to a secure footing on the seabed. With positioning confirmed, an electrical arc strikes between the electrode and the steel. The metal melts and fuses cleanly despite being fully submerged. After a pass, the diver taps the weld to listen and inspects the structural build by hand. The torch is moved, the angle changed, and the next pass goes down. A weld put together this way carries the same problem every wet repair carries. What looks sound on the outside may not be sound on the inside. The inspector is not looking for damage that already happened. He is hunting for the spot where future damage could start. After 100 meters of damaged hull plating are cut out and replaced with multi-pass welds inside and out, every joint passes under non-destructive testing, hunting for cracks and gas pockets the eye would never see. The bolt circle on a propeller blade root is one of those small surfaces where a fraction of a millimeter decides whether the blade runs true for years. A large 5-axis milling machine carries a measurement probe across the seating face of a propeller blade. Point by point, the probe records the geometry of the surface, where the blade will bolt onto the hub, comparing it back to the design tolerances before the blade is released for assembly. A part no one has ever built before still has to prove itself the same way as one built 1,000 times. A 1.35-meter propeller, weighing about 200 kilograms, was built by depositing 2.6 kilometers of nickel-aluminum bronze in 298 layers using wire arc additive manufacturing. After 3D scanning, finishing, and full sea trials, it received class approval as the world's first 3D-printed ship propeller. By the time a 49-ton rudder is being lowered into a dry dock, the metal has already passed every test it will ever face on dry land. From this point forward, the loads come from the ship itself and from the water moving around it at sea. This time-lapse from a naval refueling and complex overhaul shows the moment. A 49-ton portside rudder is hoisted by heavy crane into dry dock 11 and positioned beneath the carrier. The rudder is then rotated from horizontal to vertical and aligned to its housing in the stern. A 27-foot rudder stock weighing 20 tons is lowered separately, threading from the upper deck down through several internal levels of the ship until it seats into the rudder waiting below. Crews on scissor lifts and inside the hull check the alignment as the column drops the last few centimeters into place. Even the act of moving a finished hull around the yard runs on the same documented tolerances as the parts inside it. A vessel enters the dry dock, and the water is pumped out. Self-propelled modular transporters then slide under the hull and lift it bodily off the dock floor. The handling system is rated to a safe working load of 336 tons, with a lifting capacity of 5,500 kilonewtons. Every figure stamped on the equipment and tracked back to a certification record before a single ton is moved. The last test before a ship returns to the sea is the one the engineers carry out by hand. A bulk carrier is guided by tugs into a floating dry dock. Once the vessel is seated on the support blocks, the dock is pumped dry. Crews then work the hull, the propeller, and the rudder with high-pressure water jets to strip marine growth, rust, and old debris. The anchor and chains are lowered to the dock floor for inspection, cleaning, and painting. Fresh anti-fouling paint goes onto the lower hull and white coats on the upper section. Corporate officials and engineering teams then carry out a full on-deck and structural inspection before the dock is flooded again and the ship is towed back out to sea. Behind every certificate is a person walking the structure and reading what the paperwork claims. Around the yard, multiple jobs run in parallel. Vessels in dry dock are wrapped in scaffolding for plate renewal, grit blasting, and anti-corrosive painting. Engine cylinder heads are stripped and cleaned in the workshop. A jack-up rig is brought in by tug to the yard's berth, and a blowout preventer is craned across to it from a supply vessel. A senior engineer walks the pipework and the supporting steelwork on the scaffolding, then signs off on a helideck lighting and safety test. Sea trials are where the ship finally proves whether all the work behind it was actually correct. A new RO-Pax ferry leaves the yard under its own power and runs through stability, steering, and full-speed sea trials before the keys are handed over. A giant ship's largest parts catch the eye because of their scale. Scale is not what keeps them alive. The crankshaft holds up because its internal structure carries repeated torque, the grain flow running with the load instead of across it. The propeller holds up because its bronze recipe, blade shape, hand-finished surface, and measured balance let it move water for decades without tearing itself apart. The shaft holds up because its inner core and its outer surface both stay clean enough that no buried flaw is given the chance to grow. Every stage of what you have just seen exists for one reason. The molten pour is controlled so the chemistry does not betray the part later. The forging press is brought down so the internal grain follows the future load path. The casting mold is carved individually so the hydrodynamic shape is right the first time. The CNC tool cuts the seating face and the journals to dimensions a casting alone could never hold. The heat treatment furnace fixes the mechanical properties, and the controlled cooling locks in the right microstructure. The ultrasonic probe, the dye penetrant, the magnetic particle test, and the dimensional probe each look for a different kind of defect that the eye will not see. Every one of these steps is doing the same job in a different way, removing a failure before the ocean finds it. The strongest part of a ship is rarely the metal you can point to from the deck. It is the structure inside that metal that the engineers controlled, decision by decision, before the ship ever touched open water. Which part is more impressive to you? A crankshaft that holds up to millions of torque cycles? Or a giant propeller that turns the ocean itself into thrust? Thanks for watching. Some of the most interesting engineering on the planet happens far from the cameras. We try to bring it back. See you next time.